This lecture is a little bit different than most of the others. I'm going to call it kind of a virtual chalk talk. I'm going to be writing on the quote-unquote board here, reviewing, going over many of the principles we talked about in the last lecture and giving you practice. And although you can't respond, you're welcome to pause the video, go back over it, come and see me if you've got questions digitally, right? Make an appointment with me. This is going to give you practice. We're going to look at some standards, and you may see things like this on the exam, or at least things that are very similar. So whenever you have a Hardy-Weinberg example, you need to remember a couple of things. We're looking at a single gene. We're looking for whether or not that gene is under the influence of evolution. And we're going to start with a genotype count. So I've started here. This is a very standard one that you'll see. And then based on that genotype count, we need to figure out allele frequencies. And you remember from the last lecture, there are two ways that you can determine allele frequencies. You can use the equation where you add the frequency of the homozygous dominant to half the frequency of the heterozygotes, and that gives you one allele frequency. And then to figure out the other allele frequency, you add the frequency of the other homozygote to the half the frequency of the heterozygote. Now, the other way to do it is by just counting up all the alleles and then dividing by the total, which is how I taught my undergrad classes to do it. You can use whichever form is more comfortable. I'm going to demonstrate the first one here, and then I'll demonstrate the other one in the next example. Okay? So we're going to use this equation, and what we're going to do is we are going to say, let's put in the frequency of the dominant ones, which is 25%. These are nice round numbers. Now, it turns out that this equation works with no matter what your sample is. I like nice round numbers. It just makes the math a little easier and still illustrates the same principles. Okay, so we're going to put in our frequency. Let's make this black here. That's fine. Okay, so 0.25 is the frequency of the big A allele, right? 25%, 250 out of 1,000. We're going to add in half the frequency of our heterozygotes, which is 0.5 or half. So 0.5 times 0.5. Pardon, it's a little hard to write digitally here sometimes. So that gets us beginning. We just add that in. Half of 0.5, of course, is 0.25. So 0.25 plus 0.25 is 0.5. So our p-value is 0.5. Okay? Now, we do the same for the q-value with using the little a's. Now, because these are symmetrical, notice that the equation works out exactly the same. So 0.25 plus 1/2 right? Okay, sorry, I had a little bit of an issue there. Let me get this in. Plus, it's exactly the same. 1/2 times 0.5 equals 0.5. So our p-value is 0.5, our q-value is 0.5, and now all we have to do is plug that into the equation. I'm going to write the equation here. You should have this memorized, right? But p squared, which is a prediction for the homozygous dominant, plus 2pq, right, which is our prediction for the heterozygotes, plus q squared. Okay, and that's always going to equal 1. That's not what we're testing. What we're testing is whether each of these values match the original observation from which we derived our p and our q value. Okay, so p squared, which is 0.25 squared. I'm going to skip a couple steps here. My math teacher would be angry with me, but 0.25 squared. I'm sorry, 0.5 squared, right? Let's write it up here so I don't forget it. That's our p value, and this is our q value. That's what we calculated. Got it? Okay, so 0.5 squared is 0.25. I'm just going to write it in. Like I say, I'm going to skip a couple of steps here just to make it a little bit easier. If you want to double check my work, get out a calculator. You're more than welcome to do that. Okay. Plus 2.2 pq, which is 2 times 0.5 times 0.5, which is equal to 0.5. plus q squared, and again, because this is symmetrical, q squared is going to be the same as p squared, so 0.25 equal to 1. Now again, as long as we've not made any mistakes, these numbers are always going to sum to 1. We're not testing that. Let's look at our predictions and compare them back to our original observations. Okay, so 25%, sure enough, 250 out of 1,000. 50%, sure enough, 500 out of 1,000. Everything matches. So this is in Hardy-Weinberg equilibrium, meaning there is no evolutionary force that's acting on this. Make my R a little bit less like a V. Now it looks like a Y. There we go. No evolutionary force acting on this allele. So again, pretty straightforward, right? That works out. All right, so I've got new genotype counts here. I told you that this time I would show you how to do it the other way. So rather than using that equation of the frequencies, we are going to just count up all the alleles and divide by the total. And whichever method is more comfortable for you, feel free to do that. This is the one I use the most and I teach my students, so I'll probably use this one thereafter. So we have 490 individuals that have 2 copies of the big A allele. So we would do 2 times 490. We're just doing a raw allele count. And then we have 420 individuals that have 1 copy of that big A allele. So we're going to add in 420. Okay, so this is 980, right, if I've done my math right, plus 420, right, which is 1,400. You can double check my math. Pretty sure that's right. So we have 1,400 big A alleles. Now for the little a alleles. Now remember, this is my p-value that I'm trying to figure out here. For the little a alleles, this is not symmetrical, so it's not going to be the same as it was in the last example. So we're going to do 2 times 90, because those 90 homozygous individuals carry 2 copies. And then we're going to add in the heterozygotes that carry 1 copy of that little a allele. There we go. We're going to do this. This is 180 plus 420. We're going to get 600. And again, if you've done everything right, especially since we're starting with nice round numbers, 1,000 individuals to start with, we're going to have 2,000 alleles. And because we have 2,000 alleles, we just divide by the total to get our p-value, right, which equals 0.7. We divide by the total to get our q-value, which equals 0.3. So again, you've done everything right. You can kind of double check yourself. If those numbers add to 1, you've almost certainly done it right. Okay? Now, we're just going to plug those into the equation. I won't write the equation again, but 0.7 squared is 0.49, right? 0.7 times 0.7, plus 0.7 times 0.3 times 2. That's going to be 0.42, plus 0.3 squared, which is going to be oops, let me add that should be a plus, not an equals. It's going to be 0.09. And again, this is always going to sum to 1. Now we're going to compare back. Now, just like last time, all of our predictions, 490, sure enough, 0.49 or 490 out of 1,000. 0.42 or 420 out of 1,000. 0.09 or 90 out of 1,000. Yep, everything matches. So again, we have no force. So there's no evolutionary force acting on this allele. Now, quick aside. Just because one allele doesn't have any evolutionary force acting on it doesn't mean that applies to all of the alleles, all of the genes in this population. So one gene can be changing and evolving and the others can be effectively neutral. That's the power of random assortment and genetic recombination during sexual reproduction. Okay, I'm going to do one more example just to demonstrate what happens when we have an imbalanced one. And then we're going to look at some specific examples and how we might be able to find at least a suspect or a candidate evolutionary force behind an imbalanced equation. Okay, so here we are. My recommendation is at this point you pause the video and go through what we did in one of those last 2 examples and use either the equation or count up all the alleles and divide by the total. Pause the video now and then you can see whether you did it right. All right, so here's how we go. And I'm going to again I like the allele counting dividing by the total. So I'm going to do 2 times 200 because those homozygotes have 2 copies of that big A allele. I'm going to add in the 200 individuals that carry 1 copy of the big A allele. We've got 400 plus 200. That's going to equal 600. Okay, 2 times 600 to count all of the little alleles in the homozygotes. Add in the 200 heterozygotes that carry one copy of the little A allele. Sorry, it looks like a Z. You'll just have to remember it's a 2. So I've got 1,200 plus 200, or 1,400. Divide by the total, which is 2,000. I won't write it in here. I'm going to skip that step. But 600 divided by 2,000 is 0.3. 1,400 divided by 2,000 is 0.7. Now remember, these are similar. I think it was 0.7 for the p-value and 0.3 for the q-value, but these are similar to what we saw in that last example. Now, let's plug them into our equation. P squared, which is 0.3 squared, so we would expect to see 0.09, or 90 out of 1,000, of our homozygous dominant. But we're seeing 200 out of 1,000. Okay, 2pq, 0.3 times 0.7, which is 0.21 times 2, so it should be 0.42, or 420 out of 1,000. But yet we only have 200. And then finally our q squared, which is 0.7 squared, which should be 0.49, or 490, but in reality we see 600 individuals. Okay, and it's always going to equal 1, but we're comparing back our calculated versions predicted. Do they match our observed original versions? And in this case, the answer is no. So there is an evolutionary force. We'll just say force, may the force be with you. But no, we're talking about one of those 5 evolutionary forces. Now, without some additional information, maybe some study of this population and this gene, we don't know what it is. It could be genetic drift, just random fluctuation. If there's a clear pattern, and if we came back year after year and saw that pattern, then we'd say, oh, it's probably not genetic drift, because genetic drift randomly fluctuate things depending on population size. But it could be natural selection. It could be immigration. Maybe individuals are moving in from another population that has a biased allele frequency. It could be non-random mating, right? So natural selection, immigration, non-random mating, or it could be new mutation. New mutation is fairly random. We don't usually see a concerted or generation after generation the same mutations popping up. So most commonly we're going to say natural selection, non-random mating, or some sort of immigration force. Okay, those are going to be the 3 most common ones. Okay, so once you see this, you know a force is acting on it. And in the next example, let's see if we can narrow down some of the natural selection forces. All right, our next example. If you'd like to pause it and run through this series, that'd be great practice. If not, follow along. So we have 2 times 400 plus 200, or 1,000 big A alleles. This is going to be for our p-value. We have symmetrical, right? So it's easy. I'll go ahead and write it here anyway. I'm going to go a little bit fast, so it's going to get a little sloppy here on the computer. Sorry. Make that look more like a bracket. Okay, plus 200 heterozygotes, and we add them up, and sure enough we have 1,000 big A's, 1,000 little a's. This is easy. Our p-value is going to be 0.5, and our q-value is going to be the same, 0.5. Now you've seen this before. When we plug it into the equation, I'm going to go fast, we're going to get our p squared value, which is 0.25. Our 2pq will be 0.5, and our q squared is going to be 0.25. So we're predicting 25%, 50%, 25%. But in reality, we don't see that, right? We have very different numbers here. So there's a force acting on this. Now, what type of force is it? Now remember, I said most commonly, if we're seeing something that we can predict and look at, we're going to look for natural selection. We're going to look maybe for immigration. Perhaps, we might have a little bit of non-random mating going on, something like that. We don't know ahead of time without doing some research or getting some further information into the population. So let's assume that this is natural selection. And you might see this on a test. I might give you an equation and saying, if it's out of balance, assume it's a natural selection force that's taken this out of balance. What type of natural selection force is there? Now, I'm going to review. You should come into the class knowing this, but let's just be clear and explicit to make sure. There are 3 main types of natural selection that have different consequences when we're looking at it at the population level. Often people think, oh, natural selection takes a good thing and makes it more common till the bad things go away. Yeah, that's one kind. That's called directional selection. So with directional selection, what we would see is that maybe two of the values, maybe the big A would be going down. We'd see fewer of those generation after generation. The big A, little a would also be going down. And the little a may be increasing. That would be directional selection. That's what people standard that kind of typically think of. They say when they say natural selection, that's what they're thinking of. So directional selection is kind of the standard where we're getting rid of one of the variants and increasing and maybe even eventually fixating the other variant in the population. And if we do that, eventually we'd have no diversity at all for this gene. Everybody would be AA in this case because it's getting more and more common generation after generation. That's not really what we're seeing here, right? So then let's talk about the other two, and then let's see if we can figure out which one of the other two is present here. Okay? So, I'll just leave in. Let's write these first, and I'll leave them there. We can look at homozygous dominant. We can look at heterozygotes, and we can look at homozygous recessive. Okay? Now, one of the types, which is called overdominance, is where heterozygote increases and both of the homozygotes decrease. This tends to maintain allelic variation in the population because you can't make the heterozygotes, which is the best overall genotype, you can't make them without having some of homozygotes in the population. Okay? This is called overdominance. Okay? And it can also work in complex genetics where you don't just have a simple two allele, and that's fine. If that, it's usually called stabilizing selection. So this is overdominance or stabilizing selection. That should be a little bit of review here. Now look at what we're seeing here. In this one, we would predict a higher number of heterozygotes than our equation says. But we're seeing the opposite, right? We're seeing a lower number. We're seeing less than we predicted. And here we'd predict less, but we're seeing more, right there. Less, but we see more. So this is not overdominance. Okay? So the one last one that you need to be familiar with. And of course, there we go. In this pattern, we see fewer of the heterozygotes than we would expect and more of both of the homozygotes. And it's not always symmetrical, but in this example it is. I predict 25% or 250 out of 1,000 should be big A's, but yet I'm seeing 400. That's higher than it should be. Same thing with the little a's. It's higher than it should be. This, conveniently enough, is called underdominance. Now, if this goes on long enough and we lose all our heterozygotes, we're eventually going to end up with all homozygotes in the population. But of course, if they're still interbreeding, we're going to maintain some heterozygotes and natural selection will remove them. This might be a preliminary step towards speciation if there's some additional force that will kind of reinforce and prevent the making of heterozygotes. So for instance, if big A's prefer to mate with other big A's, we're going to get fewer heterozygotes. And if little A's prefer to mate with little A's, so then eventually they could be completely separate species and isolate their gene pools. Okay? Now, I'm going to do one last example. So let's look at what can happen. And remember that we can't, just by looking at this pattern, we can't say, oh, it's underdominance. If it's natural selection, then it's underdominance. But there are other things that could do this also. So let's go back. In fact, I'm going to erase all of these. And let's go back to our very first original practice one. Now, I'm not going to bother to work this one out completely because hopefully you're getting familiar and comfortable with this. If we work this all out, our p-value would be 0.5. Oops. Right, our Q value would be 0.5. We'd plug it into the equation. We'd say, yep, sure enough, everything is balanced. There's no evolutionary force acting on this. Now let's say something changes. Let's say that suddenly big A's will only mate with themselves. And little a's will only mate with themselves. So this is called assortative mating, and it's a form of non-random mating. It can throw off allele frequencies and cause change in the population. Okay? And let's say, just for the sake of argument, makes it a little easier, that heterozygotes will only mate with themselves. Right? So maybe this is that gecko example that we were looking at in the previous lecture, where these guys are yellow and brown bands. These guys are kind of the modeled one, and then these guys are kind of the stripy ones. And they recognize those and have a very strong 100% preference. And even if it's not 100%, we'd see shifts, but 100% just makes it more pronounced. Okay, so let's predict what the next generation would be if we see this shift where yellow-banded geckos only mate with yellow-banded geckos, mottled geckos only mate with mottled geckos, and stripy geckos only mate with stripy geckos. Okay, say that 5 times fast. So we've got 250 individuals mating with themselves. Let's say they just replace themselves. There's no advantage to these other than the mating preference. That's the only kind of bias. And so they replace themselves. And so the next generation, we would expect to see approximately 250 big A in the population from those yellow-banded geckos that mated with other yellow-banded geckos. We'd expect to see the same thing for the recessive ones. Right? About 250 little a. But what happens when a heterozygote mates with another heterozygote? Right? So when these guys mate with each other, now you're thinking back to Bio 1, maybe high school biology in your Punnett square, right? 25% of these matings would result in big A. Now, 25% of those 500 individuals would be about 125 big A. So we would add in about 125 here. Same thing for about 25% of those 500 or 125 would be little a, and the remaining 50% or about 250 of those individuals would be heterozygotes like their parents. So after one generation of completely assortative mating, we would have 375 big A's, 375 little a's, and only 250 of our heterozygotes left. Now, if you plug this into the Hardy-Weinberg equation, do what we've just been doing with these other examples, you'll find a p-value still of 0.5 and a q-value of 0.5. Those didn't change. But we've dramatically skewed the distribution of our heterozygotes and homozygotes. So this looks like underdominance, right? It looks like kind of our last example. We see fewer of the heterozygotes than we would expect to. And we see more of both of the homozygotes. But there's not a natural selection force here, although some people classify mating bias as a natural selection force. But really, this is a mating bias, and so this seems to mimic underdominance. So that is just yet another example. Okay, so with all these examples, you'll see something maybe identical, at least similar, 2 or 3 of these on the exam. You should be able to go from genotype frequencies and figure out allele frequencies. You should remember the equation, be able to plug those into the equation, get those p, the p squared, the 2pq, the q squared, compare them back to the original data from which we are working, see if there's an evolutionary force. And then you should be able to answer some questions. If I say, hey, let's assume that the evolutionary force is natural selection. Is it directional selection? Is it underdominance? Is it overdominance? Right? You should be able to recognize that based on the differences between what you are predicting and what you originally observed. Okay, so practice that. If you'd like more examples, go ahead and make an appointment with me or log on during office hours.